Okay, good morning. So we continue the lesson of the inverse of a matrix we started last time. Let me just refresh your memory a little bit. So if I give you a square matrix A, we call this invertible or non-singular. If you can find another square matrix of the same order B, so that A times B is equal to B times A, but more than that, it should be equal to the identity matrix of the same order. In that case, we call A invertible, yes? Okay. Then we learned that this is not always the case that a given matrix is invertible. For example, I don't remember the example, but you can check that. For example, a matrix like this, 2, 3, and 6, I think that was the matrix. So we learned that this matrix is not invertible, even though it doesn't have any zero entries. But still, we confirmed that such a matrix is not invertible because we assume that this is invertible and we reach to a system of equations, then we realize that that system of equations doesn't have any solutions. And then again, I gave you another example of another matrix which was invertible. So that was important to know that this is not the case that all given square matrices are invertible. Some of them are, some of them are not. And then still we don't know how can we immediately realize that a given matrix is invertible or not unless we start calculating. We will probably, if we have time for this course, we will also go to that. So that was the idea. And then we answered this question that assume that someone found a B with that property. Can that person also find another matrix, say C, with that property? And then the answer was negative. So it means that if you can find such a matrix B with that property, that is the only one. So that is, in other words, that one is unique. In that case, this B is called the inverse. So if you can find such a matrix, I would say that B is the inverse of A. And because that is unique, it deserves a symbol for it. And the symbol is better to have some connection with A itself. Okay, B is denoted by A inverse. Yes? So from now on, we say that if, this is a big if A is invertible, then, so let me write like this. A is invertible implies that A times A inverse is equal to A inverse A is equal to the identity matrix. So remember that in matrix theory, whenever you want to use the inverse of a matrix in some kind of argument in your problem, before that you have to convince yourself that that matrix is just invertible. You cannot just start using the symbol A inverse without first justifying that this really exists. That is important. Okay. Let us start with some example today. So as you see, example 155. So show that a diagonal matrix is invertible if and only if none of the entries on the main diagonal is zero. In that case, how can one determine the inverse matrix? Okay, so that's the question we want to answer. But let us try to answer it for a 3x3 matrix, because you will feel that, of course, this is not the most general case. You have to understand it for an N1A case, but this is very similar to that one. So let us just, for simplicity, concentrate on a diagonal matrix, which is 3x3. Yes, so A, B, C, and here 0, 0, 0, everywhere else 0. Okay, do you think that, and now for that, because this is if and only if, I have to go in two directions. So first assume that A is not 0, B is not 0, C is not 0. Under these conditions, do you think that this matrix is invertible? If yes, you need to justify. So if you want to show me under these conditions this matrix is invertible, you should be able to propose a matrix which can play the role of this B. So that if you multiply that matrix from both sides to this matrix, you will get the identity matrix. But can you guess what that matrix is? In principle, you should, because you know how diagonal matrices are multiplied, yes? Or do you have any idea? So can you guess a matrix here, so that when I multiply this by that and the other way around, the result of both of them is actually equal to the identity matrix?
Would it be 1 over A 0, 0, 0?
Yeah. Yeah, exactly. So that is the idea. So if you multiply this by a matrix like this, yes. If I ask you what is the product, this is, by the way, something that you need to know. If I have two diagonal matrices, we had these lessons before. If I have this diagonal matrix, I want to multiply it by this diagonal matrix, you can do it much faster by just multiplying A by C and B by D. So that is what we learned before. So of course I am just doing the same multiplication, but the result will be as if I am just multiplying these. Yes? So that's correct. So what you suggested is correct, because according to this rule, if you take this rule and then multiply it here, A will be multiplied by 1 over A, which gives you 1, but these two will give you 0, so this becomes 1. But the rest of it will remain 0, and then the same reasoning here, this becomes 1. That's correct. So if A, B, and C are non-zero, and then if I want to find the inverse becomes this. But of course, you have to convince yourself that the other way around is also true, but that is the same thing, yes? You just multiply these matrices from the other side, and then you see that this is correct. So this means that sometimes in the books you see this. Do you agree that this is correct? Let me write for 2 by 2 and assume that A and B are not 0. Do you agree that this is correct? Yes, that's the same. So it means that if you have a matrix which is diagonal and none of these entries is equal to 0, if you want to inverse that matrix, there's a simple idea. You can just inverse the numbers, yes? But of course, this minus sign here and this minus sign here is somehow some kind of abusing the notation, yes?
Does this work for every matrix?
No, that's unfortunate, yes, because finding the inverse of the matrix is a very complicated process, especially if the dimension of the matrix goes high. But this is why I'm saying that this class of matrices are very easy to work with, because finding the inverse is just simply inversing the main diagonals, yes? Okay, so if this is the case, but this question starts with if and only if, so it means that I need to consider that these conditions are satisfied and show that the matrix is invertible. We did that one. Now the other question is that if this matrix is invertible, you have to prove that all of them are non-zero. Okay, so now the other way around. So now we have to assume that. So now let A 0, 0, 0, B 0, 0, 0, C be invertible. We show that A is not 0, B is not 0, and C is not 0. Because it was expressed in the problem by the if and only if. If and only if means that Okay, first I assume this is true. I show my matrix is invertible. This is one direction. Another direction, I assume that my matrix is invertible. I have to prove that all of them are non-zero. Why is that?
Because if one of them is zero, that means that whole column will be.
Exactly, and then I have that problem. So assume that to prove this again, it's a proof by contradiction. Say this is not the case. Say at least one of them is zero. For example, assume that this is not the case and then at least one of them is zero. For example, A is zero. Then is it possible for me to find another matrix here so that it generates 1 0 0 0 0 0 1 0 0 0 1? Is it possible? No, because it doesn't matter what you put here. What a, for example, x, y, z, t, u, v, w, l, m. For example, it doesn't matter. If I take that one and multiply it here, it becomes 0. But its entry is 1, so it is not possible. It's very simple, but it's a very good idea to remember. Okay, so the next remark is that if I give you the identity matrix of order n, and I ask you what is the inverse of that matrix, what is the answer? The identity matrix itself, because we just learned identity matrix is a diagonal matrix with ones everywhere on the main diagonal. So none of them is zero, it is invertible. If I want to inverse that, I have to inverse all the entries of the main diagonal, but the inverse of 1 is just 1. So that's a very important thing. By the way, it is according to our expectations. It is like to say 1 to the power of minus 1 is 1, something like this. Okay, but let us start a little bit nicer questions. So I haven't addressed how we can determine the inverse yet. This you have to wait. If we can reach to that point, it will come a little bit later. But the questions that I am asking here are these type of questions. I am proposing the inverse myself. I want you to confirm that. Okay? So for example, here in example 157, I give you a square matrix. I haven't given you the entries, but I give you that A squared is A, which means it is idempotent. We want to show that 2A plus 3I is invertible. If I just stop there, I would consider it a really hard problem. Okay? But I haven't stopped there. I have proposed what the inverse is. So what I have shown, I have asked to show this matrix is invertible, and moreover, show that its inverse is this matrix. If I hadn't given you this part, then you should be able to guess this yourself and then prove it. So that would be a hard problem. But this is not a hard problem. Okay, I would say. Okay, so do you have any idea what to do? So let me write it down here. So you can think a little bit. So you see in the problem, I have given you a matrix A with one property, which a square of it is equal to itself. So there is a name for this kind of matrices, which is called idempotent. Now my claim in this problem is that we want to show that 2 times A plus 3 times I. I don't know the entries of A. I know that A satisfies this property. Then I make this combination. I am claiming it is invertible. So I need to prove 2 things. We need to show that 2A, show that 2A plus 3I is invertible. Moreover, we want to show that 2A plus 3I inverse is equal to the matrix given here. 1/3 of I minus 2 over 15 A. Okay, how should I prove this? Yes?
If you multiply 2A plus 3I with its own Or supposed.
Yeah. Exactly. Because the inverse is being proposed here. Yes? So that is not a hard task. What I need to confirm, because they are claiming the inverse of this matrix is this matrix. If you want to confirm that this is indeed true, what I need to do, I need to take this one which is proposed to us and multiply it by the main matrix to see if it becomes the identity matrix. But for the time being, I have to do it in both directions. Yes? We have to confirm. Okay, so, and by the way, invertibility is also proven. Yes, because it might happen that you can convince in the future, you might be able to convince yourself that your matrix is invertible, but it is a harder task to determine its inverse. So these are two different subjects I want you to understand. Okay, so sometimes we can just prove that very easily, we can prove that our matrix in the future, that it is invertible. Okay? So it guarantees the existence of the inverse, but still finding it is a different problem, yes? So there are two problems there. Existence of the inverse, which means invertibility, and the second question is that, okay, now that we know it is invertible, how can I find its inverse? So I want you to understand these are two problems. Okay, but if I can show this, I have actually two birds with one stone, because when I multiply that matrix by this and it becomes I, it not only shows that my matrix is invertible, but also shows that this one is its inverse, because the inverse is unique. Okay, so what I do, I start. I take that matrix and multiply it by that. And ask myself, is it equal to the other way around? So these question marks we need to answer. First of all, tell me, is that reasonable? If the answer to both question marks is positive, then it means that my matrix is invertible and its inverse is this one. I just want you to understand. Okay, I will do one of them. The other way around, you can do it yourself. So for example, let us check that this one is indeed equal to the identity matrix. So what I do, I start from the left-hand side and try to do some calculations. So what should I do? I want to show that this product is I. What is the first step? Multiplication, distribution is allowed, yes? In matrix theory, we can distribute. So I take that one and multiply it here, which becomes 2/3 A times I. So if you don't mind, let me write it down. And then I will take this one and multiply it here. So the answer becomes minus 4/15 A times A, which becomes A squared. And then I will take that one, multiply it here, so the answer becomes I squared. Because 3 and 1/3 cancel each other. And then this one multiplied by that one is minus 2/5, because this 3 and this 15 are simplified, 5 is left, and I times A. So we know that distribution is allowed in matrix theory. So we can just continue. But we also know that A times the identity matrix is A itself. But according to the problem, this given matrix is idempotent. So instead of A squared, I can put A. So this becomes minus 4/15A. I squared is just I times I, which becomes I again. And then minus 2/5 I times A, which is A. Yes? So then I have to simplify things. So how should I do that? This one, and that one, and that one. So what I can do, I can write A here, and I calculate these numbers. Yes? And then I have I at the end. But let us calculate this. So if I calculate this, the common denominator is 15. So 15 to this 5 times 10, 15 to this 1 times, 15 to this is 3 times. Yes, so it becomes 6. And then I have A plus I. But 10 minus 4 minus 6 is 0. So this becomes 0 times A, so it becomes the 0 matrix plus the identity matrix, that the answer becomes the identity matrix. But it is not finished yet. Because if I show that this is I, still there is no guarantee the other way around is also I, because matrix multiplication is not in general commutative. At this stage, you have to check this one as well. But that's exactly more or less the same calculation. Yes. Okay, any questions? Okay. So the reason that I'm saying this might be hard, if I haven't proposed this very particular combination coming up, by the way, there is nothing to say that this is the inverse of that one plus the inverse of that one. That is completely out of discussion, yes? But if I hadn't provided you with this, then coming up with these very strange numbers on your own is not that easy. But might be you can find it yourself in some way, but it is not that easy. But this is very straightforward. So if I give you a matrix and I propose you the inverse, you can immediately confirm it. Okay, let us solve some problems, and then of course I will give you some time if you want to practice. Okay, so what do you think about this problem? Let A be a square matrix such that we have this. It's like a polynomial, yes? It is comparable to a polynomial of degree 3. 3x cubed minus 2a squared plus 3. So it means that if you have a matrix that satisfies a polynomial, yes? So you have a matrix which satisfies this equation. We want to show that A is invertible, and we want to determine its inverse in terms of A. Okay? Okay, so why do you think? So I give you a matrix, you don't know anything about the entries of the matrix, but you know that for some reason that matrix actually satisfies this given equation. How can you be sure that this matrix is invertible? And how can you find its inverse in terms of its own in terms of the matrix itself? Why do you think it tells you that this matrix A is invertible? There is one way to think. If you want to show, this is the only way that you can do it up to now. If you want to show that the matrix is invertible, you need to convince ourselves that there is a matrix. How? I don't know. There is a matrix that if I multiply it by A from both sides, it becomes the identity matrix. Why do you think that's the case? So you need to tell me, you need to have some idea about the matrix so that when I multiply it here and multiply it here, the answer becomes I. If you can say something about the question mark with that property, then it means that you guaranteed that the matrix A is invertible. But how should I do that? No idea?
One idea would be so in the equality you have the identity matrix as one of the terms. If you can show that two products become the identity matrix, then you can have.
Yeah, but how? Yeah, the idea is correct.
So I would first probably move 3 3i to the right.
So that's a good idea. Yes, I will do that. So 3a cubed minus 2a squared is 3i. So by the way, what Alexander is actually telling is a very good idea. So sorry, this should be minus 3i. Why is that? Because you know that you want to have somehow I isolated at some point, yes? Because you want to show that the product of a matrix by your matrix A becomes I. So by the way, it's not far from expectation that let us move minus 3i there. But of course, you might say that I need I, but this is minus 3i, but that's a minor problem. What we can do, we can just divide everything by minus 3. Of course, division in matrix, here we just multiply everything by minus 1 over 3. Yes? What is the motive behind that? Because I want to make it I. So let's just do that. I multiply everything by minus 1 over 3. This becomes what? Minus a3. So I'm multiplying everything by that. And then this I multiply, it becomes positive 2/3 a squared. Yes? And then I multiply that, it becomes I. So far so good, because at least I needed a single I there, I have it. Okay, then?
We can factor out a.
Even though I can factor out a squared, but this is, I need a, and it is important to factor a out, not a squared. If I factor a out, then it becomes minus a squared plus 2/3 what? A is equal to I. But of course, you know that if you want, you can factor a from the right as well. Yes? So if I factor a from right, becomes minus a squared plus 2/3 times a. Yes? So we are done actually, yes? Because my goal was to answer this question mark. So what is the question mark here? So this is playing the role of your question mark, because I was able to find the matrix, whatever it is, I don't care, so that when I multiply to my own matrix from both directions, the answer is I. Yes? So this means that yes, A is invertible, but more than that. And A inverse is equal to what?
Minus a squared.
This is playing the role of, yeah, exactly. And that was the second part of the question, because the second part told us to calculate A inverse in terms of A itself. So that's a good idea. So whenever you have a matrix which is satisfying a polynomial, so the polynomial you can consider in your head is here. Okay, so if your matrix satisfies this polynomial, but of course this 3 will be changed to 3i, then it is definitely invertible. So that's a very good idea to have. Okay, good. Let us solve another problem. Let A and B be invertible. So this problem guarantees invertibility of both of them. But A and B are such that A plus B becomes A times B. We want to show that the inverse of A plus the inverse of B is the identity matrix. Okay, so is the problem clear? So I start with two matrices. In the problem, I guarantee that they are invertible. And they are designed so that A plus B turns out to be equal to A times B. We want to show that under these conditions, the inverse of A, whose existence is guaranteed by the problem itself, plus the inverse of B, becomes the identity matrix. That's also a very simple problem, okay? Just want to wait for you a little bit. Okay, any idea? Okay, might be it's a good idea if I give you time for these three exercises and then solve it together, okay? So I want you to think about these problems for a while, and then I come back and solve the problems for you, if you couldn't. Okay, now any progress for this question? Yes? So how should I do that?
I started by multiplying both sides of.
What is written here, yeah?
Yes, I multiplied both sides with the inverse of A, and then it means that one part of the.
Yeah, and then?
After that, I changed the identity matrix. I came there.
So let me follow yours. So what you are saying is that you multiply everything by A inverse. This is possible because if this matrix is equal to that one and A is invertible, so I can use this A inverse. So I multiply it. Of course, it's better to multiply from the left because otherwise, if I multiply A inverse from the right, I cannot flip A inverse and B. Yes, so I have to multiply by A inverse from the left if I want to make some progress. Okay, that's the first step you're saying.
Yes.
And then I multiply this in probably, so then this one times that one. This one times that one. Be careful, you are not allowed to commute. But associativity is possible. So I just remove these pair of brackets and put them around the first pair. And then you know A inverse A is I, and A inverse B is nothing I can do for it right now. But then you know that this is the identity matrix.
Hold on.
Yes?
Does that make sense?
Which one?
The second to last row you wrote.
Here?
Yeah.
Yes?
How?
Because this is the product of three matrices, and matrix multiplication is associative. So instead of putting a pair of brackets around here, I put them around the first.
Okay.
And then here, I just multiply this in. I multiply this. Okay, and then this becomes the identity matrix times B. That identity matrix times B is just B. And then I have A plus A inverse B. At least we made some progress because we need I. We have it, okay? Then?
After that, I just rewrote identity matrix to B inverse times B, and then I can factor B out on the right side, and that means that there is both B.
So you can write like that, but I just want to wait to see what you do at the end. So you write it as B inverse, and then, so, okay, and then B is equal to B. Then what?
B, since if you, or a matrix times the identity matrix is just a matrix, so we can write I times B.
I times B, then?
And since we have a matrix multiplied by B, and the identity matrix where it is equals to the identity matrix multiplied by B, we can assume that.
No, that's important. So in matrix theory, of course this is possible here, but if you just leave it like this without any comment, then you will lose some points. Because the whole point is that there are three deviations from number algebra, and one deviation is that we do not have multiplicative cancellation. So, for example, if I say AB is equal to AC, we cannot say that, okay, so B is equal to C. Yes, we had this, one of the important deviations from number algebra. Of course, in this case, it works. Yes, we talked about these things. One of the main goals of this lesson is to appreciate the difference between number algebra and matrix algebra. So, I mean, if you say that, okay, A times B is equal to A times C, there is no way else, so B has to be equal to C. If you go back to the previous notes and my videos, you will see that I gave you examples of A, B, and C for which this holds, but this does not hold. Okay? It is possible in matrices. Okay, but of course, in this case, it works, unless, but you need to justify it. Yeah, so whenever you see this, without any comments, you conclude this, you will lose some points if that's an exam, okay? If it's an exam, okay? Unless you say that A is invertible. Because if A is invertible, then it means that I multiply both sides by A inverse, and then it is not guaranteed, by the way, because we saw that this is not always the case that every matrix is invertible. So when you multiply everything by A inverse, first you have to convince yourself that this exists, and then you are allowed to use it. In that case, yes, I put the pair of brackets here, I put the pair of brackets here, but this becomes I, so it becomes B, this becomes I, that becomes C. Which is, in this case is true, but you need to give a little bit of this comment on that, so that it shows you appreciate this, okay? So that's an important fact you need to know. Okay, so what you are saying is that in this case it is correct. In this case I can really eliminate B because B is invertible. So it means that I can multiply everything from the right side this time by B inverse. And then you are right, then it becomes. So in this case cancellation was correct, but you need to leave a little bit of comment on that. Yes? Okay, but I prefer to do it simultaneously. It is shorter. So let me take this off, because that's not wrong, that's correct, but you are doing it in 2 steps. But we don't need to do that, yes, because I can start from here. A and B are guaranteed to be invertible, so I take A inverse and I take B inverse simultaneously and multiply it on both sides, yes? Yes. So what you did in 2 steps, I can do it in 1 step, yes? So is that understandable? So I took A inverse, which is guaranteed to exist, and then this is the same. I actually multiplied this from both directions by A inverse, B inverse, and I did the same thing for the others. Okay, but then multiplication works like this. So I just multiply them simultaneously. So it becomes A inverse, A B inverse, plus A inverse, B B inverse. And you know that I don't need to be very sensitive about pairs of brackets because it is associative. And then I can do this here. I can write A inverse A, group them together, and I can group B, B inverse together. Yes. And then this one is I, so it becomes B inverse. So this is I. Here, this one is I. So this becomes A inverse. And here, this is I. This is also I. So when I multiply them, it becomes I. But of course, this is exactly what I want because matrix addition is commutative. So if you want, you can commute it and then stop. But that is essentially what you did, but you did it in 2 steps. That's exactly true. But that's what I want you to be careful. Whenever you want to go from this to that, you need to make sure, you need to tell because A is invertible, I can do that. Because if A is not invertible, you cannot do that. Yes? Okay, so this is this question. Okay, we go back here. I think this question 160 is actually simple. So A and B invertible, they are invertible of the same order, and then we have something like this. We want to determine the unknown matrix X, so somehow. It's like in numbers, I want you to practice on this algebra a little bit. So what is this? I have A times X plus A, and then I have B inverse, and then I have C on the right-hand side. So the goal is actually to determine the unknown matrix X in terms of A, B, and C. So what should I do? It's comparable with this algebraic equation, yes? A times X plus A times B inverse is equal to C. So more or less, it's the same thing, but you have to respect the algebra for matrices. That's the only difference, okay? So how should I do that? It is guaranteed, yes, that A and B are invertible. Okay, so what should I do? I want to isolate my X. Yes?
I start off by multiplying the left side with A inverse and the right side with B.
B. Yes, that's good. So I start multiplying A inverse from the left and B from the right on both sides, yes? Because multiplying this by this will actually take that A away, multiplying B to this will take that B inverse away. Okay, so then what happens? So let us just do it in our head. So I multiply here, and I multiply this there, so it becomes x plus a. But I have to respect the order on the right-hand side. I multiplied a inverse from the left, so here I also have to multiply a inverse from the left. I multiplied b on the right, so I multiply b. And that's it. I want to find my x now. So what is x? X is a inverse cb minus a in exactly the same order that appears here. You cannot change the order at all. So this should be the only way that you write it, yes? Okay, so that's also good. And the next problem is actually an important problem. As you see in the remark, I have seen that, okay, if you can come to that point, this relation becomes an important relation in the future. And by the way, the nature of this problem is interesting. So you see that you have a matrix which is sandwiched between a matrix and its inverse, if that matrix is invertible, and then you want to raise it to some power. It's very interesting. This power will not affect the left matrix and the right matrix, it only affects the middle one. Then we raise it to power n. Okay, so how should we prove that? Before proving it rigorously, hopefully you know what is the rigorous proof of that. What is that? There is a general method for solving this usually, yes? Induction, yes, because that is n and n is a natural number, yes? Okay, so, but before doing mathematical induction, let us try to understand what is going on. So this tells me that if I have a matrix A, and if I have P, P is invertible, okay? Then, if you take P inverse, which is guaranteed to exist, and multiply it by this A and multiply it by P itself, and you decide, for example, to raise it to power 3. It means what? It means that you have to multiply the same matrix 3 times. Yes? This is the meaning of raising this matrix to power 3, for example. But then you see this combination is nicely designed or engineered. So what is happening? So these two in the middle cancel. So this becomes I. And don't worry about pairs of brackets because it is associative. So if you respect the order, it doesn't matter how you group them. And then again, this one is also I. And then what is happening? P minus 1 is left. A times I times A times I times A times P. Yes? But then A is just A to power 3. Yes? Because A times I is A times I is A, so I have 3 A's multiplied, so it becomes A to power 3. So this means that this is the idea behind this problem. So because if you write them in a sequence, one after the other, then P inverse in the middle, they cancel each other out. Okay, but this is not a proof, but that's the idea of the proof. So if you want to prove it, you need to use mathematical induction. So how should I prove that? So I would say that, okay, let me call it this Pn. Pn is P inverse A, P to power n is equal to P minus 1, A to power n, Pn. We have to check the truth for 1. Yeah, so what does it mean? It means that I have to see if this statement is true. I replace every appearance of n with 1 everywhere, yes? So is this true or false? This matrix to power 1 is P inverse P AP, and this A to the power of 1 is itself, so that is trivially true. And then we assume that P of K is true. It means that P inverse A P to the power of K is equal to P inverse A to power K P. Yes, assumed to be true. And then I have to prove that this is also true for P of K plus 1 is also true. So this means that I have to show to be proven, yes? But this is, I think, very easy. What is your suggestion to start to prove this? My goal is to prove this last equality. So might be it's a good idea if I start from the left-hand side, use my assumption to reach the right-hand side, yes? So I start from the left-hand side of this and show the left-hand side is equal to the right-hand side. So how should I do that? I would say that, okay, the left-hand side is equal to p minus 1 a p to the power of k plus 1. Okay, so what is the first step, do you think? Because I want to do it in a way that I can use my assumption. Yes?
Separate so it's speed.
To the power of
Yeah, to the power of
k and then times 1 more, yes? So this becomes p minus 1 a p to the power of k times another one of them. Yes? But now I can use my assumption because you see, this one is assumed to be p inverse a to the k and p. So instead of that, I put p inverse a to the k and p, and then I multiply it by p inverse a p. But what I can do now, I can use associativity to group p and p minus in the middle, and then this one. But then immediately I see that this is I, so this becomes p inverse a to the power of k a p, but this is nothing except a to the power of k plus 1, and then p, and that's exactly equal to the right-hand side. Yes? So I was able to show that this is true. Yeah, hopefully we can reach to that level that we use this identity. Okay, so I think it's a good point to stop here. We continue the lesson next week. And I think next week the lesson is not here, so I don't know what we are supposed to do for recordings. Yeah, we will manage it, but I think it should be in another room. They have this own proof here. Yeah, any questions? Thank you.